So this next lecture for physiology is the respiratory system. And lucky for you, you guys have learned a little bit about this system already when we talked about carbon dioxide and protons and acidity buildup in the blood. So we're going to actually go ahead and learn the details of it now. Don't forget that the slides that are hidden, you are still responsible for, but I'm not presenting them because they're just basic anatomy. And again, you should know this from your anatomy course. So respiration has 4 steps: ventilation, perfusion, diffusion, and regulation. Ventilation is the physical movement of air from the outside environment into your mouth, down your trachea, and into your lungs and alveoli. Once the gas gets into the alveoli and it moves into the alveolar space to cross the alveolar wall, that's called perfusion. And then diffusion, you guys know this term. It's going to be the movement of oxygen from alveoli into blood and the movement from carbon dioxide back into the alveoli. The last process is going to be regulation. And regulation is just your respiratory muscles and nervous system interacting together to allow you to inspire and expire proficiently. So it's going to start off at the nostril, moving into the nasal cavity, and going back and into the larynx, down the trachea, into the bronchi, through the bronchioles, which are these smaller branches, until it reaches the alveoli. Now, along that pathway, you're going to have a good amount of mucus tissue as well as cilia. The mucus is there to humidify the air, and then the cilia is there to filter the air, because by no means is the air that you breathe fully clean. Now, respiration itself includes 4 parts to it. The first one is pulmonary ventilation. This is the physical movement of air in and out of the lungs between the environment and the alveoli. Then you have external respiration, which is the diffusion of gas from the alveoli into the blood and then blood back into the alveoli. Then we have the transport of the gas. So once oxygen goes from alveoli into the blood, that oxygen is going to move through the blood and get delivered to the tissues that it needs to go to. And at the same time, the blood is going to pick up the carbon dioxide from the tissues and circulate it back through the veins, going back to the heart. Internal respiration is that process of gas exchange between the blood and the tissues itself. Now, what exactly is happening at the alveoli? If you notice, I did skip a few slides. I want to start with alveoli because that's really where the physiology is happening. So you go through the trachea, down the bronchi, through the bronchioles, and at the tips of the bronchioles, you have this grape-like looking structures called alveoli. Now, inside the alveoli, you have like a thin layer of oil-like covering we call surfactant. This is a very important ingredient we have. Surfactant is the oil-like covering that decreases the surface tension of this balloon-like structure to prevent it from collapsing. Now, just like capillary beds, how many cell layers thick is a capillary bed? Well, 1. Same thing with an alveoli. It's a single cell layered thick, simple squamous epithelium. Now, why do you think it's important to have simple squamous epithelium? What did we say it's easy to do across this? Correct. If you said diffusion. It's easy to diffuse gases in and out of the alveoli. You don't want to make it difficult at all for your body to move gases. And what you see here is that surrounding all the alveoli is a system of capillary beds. This capillary network is where the gases are going to diffuse in and out of. And then inside the alveoli is where you're going to have the surfactant. So in terms of the physiology of cell function of the alveoli, there are 3 cells that make up alveolar walls. One of them is called a squamous alveolar cell. This is the basic type 1 alveolar cell. That simple squamous one that I told you makes up most of the membrane. And this allows for easy gas exchange and easy diffusion. A second type of cell that you have in the alveoli is called a great alveolar cell or a type 2 alveolar cell. These guys are not flat. These guys are cuboidal cells and they make up 5% of the surface. And their job is not for diffusion of gases, but to provide aid to the type 1 cells. So if the type 1 cells get damaged, the type 2 cells are able to repair that epithelium. And these guys also have a second really big job in addition to helping the type 1 cells, and that second big job is to secrete surfactant. So these are the cells that actually make the surfactant. And like I said, surfactant is like an oil-like substance, so it is hydrophobic. What it's actually made out of is phospholipids and proteins. Again, this liquid covers the inside of the alveoli and prevents it from collapsing during exhale. So when gas leaves the alveoli, think of gas leaving a balloon. Generally, when gas leaves a balloon, it shrivels up and collapses. Surfactant is what prevents the alveolar balloon from collapsing. The third cell is our customized immune system cell for the respiratory system. It's called the alveolar macrophage. Macro means big, phage means it does phagocytosis, and this is the most numerous of all of the cells in the lungs, and these guys are mobile macrophages, which means they can walk around all of your respiratory system looking for anything they don't recognize and phagocytizing them. So here's our illustration. Follow my pointer. This is the type 1 alveolar cell, so simple squamose. Here's your type 2 alveolar cell, so your cuboidal cell, that makes surfactant. And the type 3, which is called the alveolar macrophage, and this is your immune system cell, and it's able to move around in the alveoli, phagocytizing any bacteria it doesn't recognize. Now this little sucker here, this layer here, is a single layer of phospholipid. This single layer of phospholipid is what we call surfactant. This is what lines the inside of the alveoli, preventing it from collapsing. Now, in order to move air in and out, you need the use of two main muscles. Muscle 1, the diaphragm. Muscle 2 is going to be the muscles in between the ribs, and these are called intercostal muscles. You have two layers of intercostal muscles, the internal ones and the external ones. And the external ones help to pull the rib cage up. The internal ones pull the rib cage down. Now, when you're going to breathe in air, you want to create a low pressure system inside your lungs. Why is this? Well, write this down. Gases always want to move from an area of high pressure to low pressure. That is the rule of gas movement. So if that's the rule, and our goal is to get gas to move into the lungs, you want to make sure it's low pressure in here. And one of the ways to make this area low pressure is to increase the volume or the space inside of it. So to increase this thoracic volume, you're going to not only take the diaphragm and contract it down, but you're going to take the rib cage and pull them up. This is going to open up a space in here, dropping the pressure, forcing the air to move in. The opposite is for this one. If you want to exhale air, you want to generate a high pressure area here, because if this is higher pressure than the outside, the gas is going to want to move from here, back out the trachea, and out of your mouth to exhale. So again, you're going to move the two muscles. The diaphragm here is going to relax upward. This is the direction of diaphragm relaxing. So it's going to push up in the thoracic region. And then the rib cage is going to pull back down using the internal intercostal muscles. Essentially, you're squeezing the air out of this compartment and out. So this is just another illustration of what we just talked about, and I threw in some numbers for you. So ignore this part of it for now. Let's just look over here. PB means barometric pressure. This is the pressure in the external atmosphere. We're going to assume that our net pressure outside is a 0. This is just going to be our reference point. Pressure is not actually 0 outside, but this is just our reference point for this example. The PL is the alveolar pressure. Now remember, gases always want to move from high to low pressure. If the pressure in the alveoli is 0 and the pressure externally is 0, is gas going to prefer to move either in or out of the lungs? No, there's no net movement. But what if I took the alveolar pressure and I made it a -1? So from 0 to -1, I lowered the alveolar pressure. And we know from this last slide that a way to lower pressure in here is to increase the volume in here. So expand the ribs out, contract the diaphragm down, increase the thoracic volume to make the pressure in here drop. So when you do that, you see these arrows. This means the rib cage is pulling out, the diaphragm is pulling down, allowing the pressure inside of here to be a -1. Remember again, gas always goes from high to low pressure. At this point now, the external pressure of 0 is higher than that of the inside of -1, so gas is going to move in. You can follow the same example on your own on the right side. This shows you equal pressures on the inside and outside, so no net movement. But then when the rib cage pulls in and the diaphragm relaxes up, it increases the alveolar pressure up to 1, and gas is going to want to move from this region out toward the lower pressure region. Now, this term compliance, what I really think is important from this is just to understand the definition. So when someone complies with a set of regulations, they go along with those regulations with ease. They don't provide any kind of resistance to it. This is the same thing in lungs. When your lungs are compliant, they are easily able to inflate and deflate. This means your lung tissue is healthy, you don't have tumors inside of it, you don't have fibrosis inside of it, you don't have fluid buildup inside of it. So the greater your compliance, the easier it is for you to inhale and exhale. If you do not have good compliance, it is usually because you have fibrosis in your lungs. This is one of the big things with the coronavirus. It can cause fiber buildup in your lungs, and this is irreversible. So fiber buildup it essentially means decreasing the compliance because you have less elasticity in the lungs to inflate and deflate. Then you have pulmonary edema, buildup of fluid in the lungs, and then the general respiratory distress syndrome, which is really an umbrella term for anything that can cause respiratory issues. Now, this is an important illustration. So this illustration is important because we would have done this in lab. I'm not sure exactly what we're going to do for the lab portion of the respiratory system yet, but it will probably be something that involves this graph. This is called a spirometer graph. A spirometer is a tool that measures your breathing volume. So you put your mouth on the spirometer and you breathe in and out, and you can check what volume of air you're breathing in and out. You can take a big deep breath in and a huge breath out, and you can see how much air is moving in and out again. So I'm going to walk you through this graph. The first two breaths that you have here, these are called the tidal volume. This is your basic resting breathing. So you breathe in, breathe out. Breathe in, breathe out. No stress, no forcefulness, nothing like that. Daily normal breathing is here. Then let's say you breathe out your normal breath. Is that all the air you have you can breathe out? Probably not. You probably still have some air left inside your lungs. So you forcefully breathe the rest of that air out. And that forceful breath out is called your expiratory reserve volume. So the volume that you have on reserve to expire out. Let's look at the other definition, I guess not the other definition, the other side of this. So let's say you take a normal breath in, normal breath out, normal breath in, but that's definitely the maximum you can take in. So from the normal breath in, you force yourself to inspire as much as you possibly can. So you take a really deep breath in. That's called the inspiratory reserve volume. From that maximum breath in, you are then told to push all of the air out. This whole volume here of what you can control in and out is called your vital capacity. The word vital means life. So this is the capacity that's vital to life. Now, if we look down here, when you forced all that air out here and here, did you empty your lungs completely? Well, no. What would happen to your lungs if you emptied them completely? Well, your lungs would probably collapse. So you have this volume that's left behind called the residual volume. This is the volume that you cannot control. And then you have a minimal volume. This is the volume you need before your lungs collapse. Do not memorize these numbers. I just want you to understand what each of these curves means and the terms that associate with them that's on this graph. So I skipped the part that has the written portion on it because I'm just going to go ahead and explain this to you rather than reading off slides. First thing I want to do is not read these guys, but to show you this picture. This graph is a depiction of percent of oxygen content versus percent of oxygen saturation of hemoglobin. X-axis means how much oxygen you have in the air you're breathing. The y-axis means how much of that oxygen is bound onto hemoglobin. Because as you know, oxygen is a gas that moves through the blood by binding to the hemoglobin of red blood cells. This graph makes sense because as you increase the amount of oxygen in the air that you breathe, you're going to have more oxygen binding to hemoglobin. So this is called an oxygen hemoglobin dissociation curve. So as you go more to the right on the curve, you have more oxygen bound to hemoglobin. As you go left on this curve, that means it's less oxygen bound to hemoglobin. So you could say it's more dissociation from hemoglobin. So again, as oxygen concentration increases in the air, that concentration dictates how much oxygen is bound to hemoglobin. So for example, at 40 mmHg of oxygen, we follow up, and it's 70% saturation. That means 70% of the oxygen that's in your blood is bound to hemoglobin. The other 30% might be dissolved in the plasma. It might be bound to the tissues. So why am I teaching this so slowly? Well, because we're going to take this curve and we're going to shift it to the right and to the left. What in the world does that mean? So here's your regular dissociation curve that we saw on the last slide. But on this slide, we're going to start talking about how different factors can affect hemoglobin dissociation from oxygen. Are factors like pH, temperature, and fetal versus adult hemoglobin. This slide here talks about what's called the Bohr effect. This is going to be an effect of pH changes. So the pH of our normal blood is 7.4. Sometimes the blood can become slightly acidic, so 7.2, or sometimes it can become slightly basic at 7.6. I'm going to change my clicker to a pen. And what we're going to look at right now is the dissociation of oxygen from hemoglobin at different partial pressures of oxygen. So let's just say we're looking at partial pressure of 40. So as you move up, you're going to have a dissociation of around 75%. So at pH of 7.4, the hemoglobin saturation is about 75%. That means at pH of 7.4, when the PO2 is 40, the hemoglobin saturation is going to be 75%. When that pH drops down to 7.2, you notice that at the same PO2 of 40, we hit the 7.2 curve here, and we see that the hemoglobin saturation dropped down to about 65. This means that less hemoglobin is bound to oxygen. So that means the hemoglobin let go of the oxygens because maybe the tissues needed more oxygen. Remember that we kind of started learning about how CO2 and pH are related. When you become more acidic, that usually means your concentration of carbon dioxide increased. If you have more carbon dioxide in your blood, hemoglobin is going to say, okay, I think it's time for me to release more of my oxygen. And that's why the hemoglobin saturation drops down from 75 down to 65. We had a 10% decrease in hemoglobin saturation of oxygen because now you don't want oxygen to be bound to hemoglobin. The point is, the more oxygen you need in the tissues, the more hemoglobin is going to release those oxygens, and therefore hemoglobin will be less saturated with oxygens. So, it's safe to say that when pH drops down and becomes more acidic, the hemoglobin saturation also goes down. And you can write this statement down. As hemoglobin saturation decreases, that means less oxygen is bound to hemoglobin, which usually means more oxygen is being released to the tissues. Now, if I extend this line higher, we see that it hits my more basic pH right here, and it increases my hemoglobin saturation to about 85. So as your blood pH becomes slightly more basic, the hemoglobin saturation increases. Usually when your blood becomes more basic, that means you already have a lot of oxygen being released out into the tissues. So if you already have a lot of oxygen, does hemoglobin need to release even more oxygen? No. Hemoglobin can stay bound to the oxygen, so we're going to see an increase of 10% in the hemoglobin saturation. Now this is all pH changes. Let's look at temperature changes. Let me get my pen again. And temperature changes, normally we run at about 38 degrees Celsius. So let's say we're looking at a PO2 of 20. And I'm only choosing 20. It's an arbitrary number. It doesn't actually mean our oxygen content is 20. I'm using 20 because as I move the line up, it'll intersect with all of my temperature points. So at my basic body temperature, at a PO2 of 20, what is my hemoglobin saturation? I would say around 28%. What happens though when your body temperature goes up? Let's say your core body temperature increases to 43. At this point, the hemoglobin saturation drops to around 15%. Now, why do you think that as body temperature rises, less oxygen is bound to hemoglobin? Well, think about what happens in your body when it's really hot. Your heart's beating faster, so more muscle activity there. Your respiratory rate is higher, so more muscle activity there. And you're probably releasing more energy as sweat, so requiring more energy there, which means you're requiring more oxygen. It would benefit you to get your hemoglobin to bind less to oxygen. So we want to lower the hemoglobin saturation of oxygen down by about 10%. This means that you have less oxygen bound to hemoglobin and you're releasing more oxygen. Good to release that oxygen because as you release the oxygen, that oxygen can be used by tissues like your heart and respiratory system. The opposite's going to happen when you lower the body temperature to 20 or 10 degrees Celsius. These are very, very low for body temperature, very bad for you. And if you're at 20 degrees Celsius, your saturation goes up to 75% because you require less oxygen to function. And at 10%, you go to 95%. So as temperature increases, hemoglobin saturation decreases. As temperature decreases, hemoglobin saturation increases. So we have two examples of that. The last piece of this is going to be fetal hemoglobin. And if we just look at a point of, let's say 40, we'll go back to 40. As we put that line up, who's holding on to hemoglobin tighter? Adult or fetus? I'll give you a second here. So again, who is bound to hemoglobin and oxygen more tightly? If you said fetal hemoglobin, you would be correct. Fetal hemoglobin has a 90% saturation rate. That means 90% of hemoglobin is bound to oxygen. which means there's not as much oxygen being released to the tissues. The adult hemoglobin is saturated at a 74-ish%, which means 74% of hemoglobin is bound to oxygen. You're releasing more oxygen to the tissues. And this is your review slide. You can just review over these shifts. This top graph shows you what it means when your graph shifts to the right. The bottom graph shows you when the graph shifts to the left. The way it always makes sense for me is to pick an example point, draw a line going up, and this shows me that the original point had a higher saturation than the shifted point. So this tells me when a graph shifts to the right, I'm going to have lower hemoglobin saturation. All right, so this slide and the next slide, they basically show you the same thing, but I'm going to go through this slide first. You kind of know this already based off of the blood and heart PowerPoints we've gone through, but let's go through it again. Let me get my laser pointer ready, and this is what we're going to talk about. How carbon dioxide moves around in your blood. Many of you might say, well, CO2 binds to hemoglobin just like oxygen does. Well, you're right, but it happens at a much lower percentage. Hemoglobin much prefers oxygen over binding to carbon dioxide. He's not really a fan of binding to carbon dioxide, to be honest with you. So CO2 needs to find a different way to move through your blood. And what CO2 does is it shapeshifts. This is really cool. I love this process. So let's say your tissues produce carbon dioxide. Here's that carbon dioxide going into the blood from the tissues. The CO2 has two options here. Either stay in the plasma and dissolve yourself, which only 7% does because CO2 is hydrophobic. What does that mean? That means it doesn't like water. And when CO2 is hydrophobic and doesn't like water, it's not going to want to be in the plasma because what is the plasma mostly made out of? Water. So very small amount dissolves in plasma. The remainder of it will go into the red blood cell. So 93% goes into the red blood cell. So you're thinking, wow, yeah, 93% is binding to hemoglobin. Nope, not right, because you again have two options. That CO2 in the red blood cell can either, yes, bind to hemoglobin, just as CO2, which only 23% does. Again, not the majority of it. But the majority of it, 70% of carbon dioxide, gets converted into this thing called carbonic acid. Write that down. H2CO3 is carbonic acid. Now, sounds kind of scary because it's an acid, but not to worry. This carbonic acid is going to change its form. But before we move on, let me just point out this enzyme here, carbonic anhydrase, ends in ase, which means it's a what? It's an enzyme. Carbonic anhydrase is the enzyme that converts CO2 into carbonic acid. I will be writing down the full equation for you at the end of this, so just give me 1 second. So CO2 converts into carbonic acid by carbonic anhydrase. Carbonic acid then spontaneously, meaning it doesn't require any enzymes, dissociates into a proton and bicarbonate. You've heard the word bicarbonate before. What do you know that bicarbonate acts as in your body? It acts as a buffer. Are these good or bad for you? They're really good for you because what is their job? To regulate the pH of your blood. Protons. Again, are these good for you or bad for you? Well, it depends on how much of them you have. But the more protons you have, what do you become more of? You become more acidic. So what happens to these two molecules? Bicarbonate comes over here. It goes through an antiporter, and it does a process called chloride shift. It brings in one Cl ion and pumps out a bicarbonate. Why do we bring in the Cl? Well, it's a negative charge. You got to make sure if you're pumping out a negative, bring in a negative. We have to maintain the charge of the red blood cell. It is very important. So bicarbonate gets pumped out of the red blood cell and goes in the plasma. Great for us, because now we can buffer our blood plasma. The proton gets removed from the red blood cell, but it can also stay in the red blood cell. Basically, what this means is that the more CO2 you have, the more that's going to go through this process and produce more protons and more bicarbonate. Bicarbonate gets pumped out of the red blood cell, and protons, some of them will get removed out of your body, but if it starts building up past the threshold, these protons will start building up in the red blood cell. And when you have a lot of protons building up in the red blood cell, what does that cause your red blood cell to become? Acidic. So then you say if you have a lot of CO2 buildup, your blood is going to become acidic. So let me switch to a pen. Let's see how well I can write this. So CO2 gets converted into H2CO3, and that breaks down into H plus and bicarbonate. This is your equation. Now the only thing you could be adding on this is the enzyme right over here. And that enzyme's name is carbonic anhydrase. Remember, this process happens spontaneously. Now, key thing to remember here is all of this is reversible. So when you first get CO2 in your blood, it turns into this so it could transport. The whole point of this is because CO2 is hydrophobic. It doesn't like to be in the blood, which means it's going to go through this whole process to convert into protons and bicarbonates. These are the forms that will transport from tissues to the lungs. Once you get to the lungs, do you breathe out protons and bicarbonate? No, you breathe out CO2. So you take this whole reaction, you reverse it back into carbon dioxide, and that's what you breathe out. That is what this picture is showing. So we're going to go through the whole process again. If you're confused, it's okay. This is the first time you're learning this, and it's virtual, so bravo to you for even working as hard as you are to learn this stuff, especially since it's physio. But I'm going to go through it one more time, really slow from beginning to end. If you still have questions on this, please, please, please send me an email and let's FaceTime or let's Zoom, because it's actually helping a lot of the students who are doing it already with me. So I can teach it to you one-on-one if you need. But for now, let's do it one more time. Let's see where you stand at the end of this. You breathe in air. That air has oxygen. Oxygen goes into your alveoli, diffuses into the blood. Oxygen loves traveling in the blood by binding to hemoglobin. They're best friends. This is the desired method. This red blood cell with oxygen bound to hemoglobin will travel through your blood until it gets to a tissue that needs oxygen. So because of a diffusion gradient, high oxygen here in the blood, low oxygen in the tissues, hemoglobin will unbind from oxygen and diffuse that oxygen to the tissue. Now, oxygen is used by the tissue. What is the gas that is produced as a byproduct? CO2. The tissue makes CO2, and this is where we're going to go through the process. CO2 goes from the tissue into the blood again. Some of it gets dissolved in the plasma, not a lot. The rest of it goes into the red blood cell. From the CO2 that got into the red blood cell, again, a small amount will bind to hemoglobin. The majority of it goes through this process. CO2 binds with H2O, that's a new piece of information for you guys, and with the help of carbonic anhydrase, turns it into carbonic acid. This spontaneously dissociates into bicarbonate and a proton. The bicarbonate leaves the red blood cell and goes into the plasma using what's called a chloride shift. This is an antiporter. The proton binds to hemoglobin, which means the more CO2 you have building up, the more protons you're going to have in your red blood cells, making them more acidic. This red blood cell will go through the blood until it gets to the lungs. And at this point, we need to reverse the whole thing. So where I'm going to start with you is right here. To reverse this whole thing, we have to do a reverse chloride shift. Pump a chloride out, bring the bicarbonate back in. Hemoglobin will release the hydrogen. Hydrogen and bicarbonate, now freestanding, will bind together to make carbonic acid. Carbonic acid will release the water to turn back into CO2. You'll also get the CO2 released from hemoglobin, and all of that will diffuse back out into the alveoli. So make sure you're able to follow along with this whole process, specifically the CO2 exchange part, because that was the physio that I just taught you. Now, in terms of regulation of respiration, what controls respiratory regulation? Well, number one, higher centers of the brain. You can voluntarily control your breathing rate. You can get yourself to breathe faster, hold your breath, breathe slower. All of that is done by the cerebral cortex. And also speech, emotions. You have pathways like sympathetic, parasympathetic will cause positive and negative regulation of respiratory rate. Now, where am I pointing to here? This is the brainstem, cerebellum, cerebrum up here. You got the pons and medulla right over here. This is called the respiratory center. It is found between the pons and the medulla. So this is where we're sending all of our signals to control respiratory rate. Now let's go through each one of these, and you'll see the arrows with either pluses or minus signs. That means it either increases or decreases respiratory rate. First one, chemoreceptors. These guys recept chemical changes. Now from what you learned, when you have a lot of CO2 in your blood, what does it get converted into? A proton and bicarbonate. The more CO2 you have, the more protons you're going to make, which means the lower your pH is going to be. This will trigger an upregulation of respiration to breathe faster. Why are you breathing faster? Well, because you're trying to breathe off all that CO2 so that you can bring the pH back to normal. Low levels of oxygen. The chemoreceptors will notice that they're binding to less oxygen. So less oxygen, again, upregulate breathing. Herring-Brauer reflex. The more you stretch out your lungs, you have mechanoreceptors in there that sense the stretch of the lungs. The more these are stretched out, the more your brain thinks, hey, if they're stretched out, that must mean there's already a lot of gas inside. We should lower respiratory rate. People with COPD are people who can generally breathe in easily, but when they try to breathe their air back out, they only breathe out a fraction of that air, which means air keeps getting left behind in their lungs and slowly starts building up and stretching out their lungs, which means that their lungs send a signal to the brain to lower their respiratory rate. The last two, proprioception and nociceptors. When activated, both of these will increase respiratory rate. I'm going to let you guys read through this. This is just what the last slide says. You've seen these slides before. If you go through one side, you'll know the other. Just the bottom of this, if your pH drops, that means you're acidic. If you're acidic, you have a lot of protons, which probably means you have a high amount of CO2. Because of this, you stimulate the respiratory center to increase respiratory rate. The more you breathe in, the more CO2 you can get out and more oxygen you can get in. And that's going to essentially, over time, increase your blood pH back to normal. Now, what if we have respiratory sicknesses, diseases, bad habits? What does that do to your lungs and your respiratory rate? Well, smoking. This is a very, very common bad habit. Smoking, there's a lot of reasons why it's really bad. Number one, it has a lot of carcinogenic chemicals in it. And people might be saying, well, a lot of things that we deal with in life have carcinogenic chemicals in them. So what makes this worse than others? Well, essentially, when you light the end of a cigarette and you breathe in, the burning of the tobacco and the chemicals causes an increase of carbon dioxide buildup. So what are you actually breathing in? Well, in addition to all the other bad stuff in cigarettes, you're breathing in not oxygen, but CO2. I'm going to go back to this slide. If you're breathing in CO2 instead of oxygen, you're building up the CO2 concentration here. A lot of CO2. Can you tell me, how does CO2, generally, in a healthy person, go from the blood back out into the alveoli? What is the process that, by passive movement, allows CO2 to move from here into there? Diffusion. Now, what happens if I start breathing in CO2 straight up, building up my CO2 concentration here? Is the CO2 from here going to then voluntarily want to go into the lungs again to be breathed out? No, because now you've shifted the diffusion gradient. So where's CO2 going to stay? In the blood, which means what is your blood going to be? Very acidic. And acidity in the blood causes cellular and DNA damage. And that is one of the reasons why you have an increased chance of getting cancer. Now, cystic fibrosis, this is going to be a mutation in a single base in the CFTR gene. CFTR is a regulatory protein that allows for the movement of chloride in and out of the lungs. So here's the deal before I start this. I'm going to kind of give you background. In your lungs, you do have mucus in them. It's a good thing. Lungs, respiratory system, they're all mucous membranes. And mucus is a mixture of something called mucin, which is really sticky like gum paste, with water. So water is mixed with mucin to break it down a little bit, to make it a little bit more fluid, more lubrication-like. So the way this works is moving chloride ions from the outside of the lungs to the inside of the lungs. Once I do that, if chloride moves into the lungs, chloride is a salt. What else is going to follow it? Well, just like anything else, water follows salt. So as chloride moves into the lungs, the water follows right behind. And when water gets into your lungs, small amounts, it's able to break up the mucin to turn it into mucus. So in someone who has a mutation in this channel, what they're not able to do now is move chloride into the lungs, which means what else is not getting into the lungs at this point? Well, water. If you don't have a little bit of water in the lungs, you're not going to be able to break up that mucin. So what it's going to feel like in the lungs at this point is like a sticky gum paste in there. And when it gets really sticky in your lungs, people with that kind of condition can trap a lot of bacteria and develop respiratory infections. But not only that, the buildup of mucus can block the movement of gases. So people with cystic fibrosis, although it's only a single base pair mutation, causes a life-threatening disease. Now let's go over the physiology of gas concentration. So a good amount of this will be a review, but some of it might be new information. So here is the equation, my friends. CO2 plus H2O gives you carbonic acid, and that breaks down to bicarbonate and a proton. This is the way carbon dioxide likes to travel in your blood. Eventually, when it gets back into the lungs, it takes protons and bicarbonate, converts them back into carbonic acid, then breaks it down into water and CO2. The water stays in the blood because, of course, you need water in the plasma, and CO2 gets breathed out. This is just a little review of what happens once that carbon dioxide gets back to the lungs. Now, what adjusts the rate of oxygen unloading? Well, this kind of has to do with those oxygen dissociation curves. So we're looking at 3 factors that can cause oxygen to unload off of hemoglobin more or less quickly. The dissociation curves do show something similar. So dependent, number 1, on how much atmospheric oxygen you have, that will determine how much is bound to hemoglobin. So if you have very low oxygen in your tissues, that means your tissues are deficient in oxygen and they really want the oxygen. If your tissues really want oxygen, no problem, my friends. Hemoglobin will release the oxygen to go into the tissue and supply that tissue with oxygen so it can do whatever type of metabolism it needs to do. Temperature. If the tissue has high temperature, it's going to also promote oxygen unloading from hemoglobin. So the hotter your tissues get, it usually indicates that they are contracting or you're working out, which means that they're going to demand more oxygen to keep functioning. And then pH in the tissue. If the tissue has a huge buildup of carbon dioxide, CO2, as you already know, causes a buildup of protons, which lowers the pH. When pH drops in the tissue, remember, all three of these are talking about in the tissue, not in the blood. If pH drops in the tissue, that is also going to promote oxygen unloading. This last one is the most potent stimulus for oxygen unloading. Now, a few terms here: acidosis, alkalosis. Acidosis is when your blood pH is lower than 7.35. Alkalosis is when it's above 7.45. This range of 0.1, that's your happy range. Once you reach acidosis or alkalosis, you won't go into shock immediately, but if it stays in that state, your tissues will stop functioning. Your blood pH will eventually cause you to go into shock. Now, what causes acidosis or alkalosis? Well, when CO2 is too low or when CO2 is too high. Let's start with this one first because this is the one we're familiar with. Hypercapnia, very high CO2. If you have a lot of CO2, you're going to make a lot of protons, which means you're going to become acidic. Hypocapnia, this is when you have very low CO2. If you have low CO2, you're going to revert the equation away from developing a lot of protons. And if you have too few protons in your blood, that's also not a good thing. And that can cause alkalosis, meaning becoming very basic. So all four of these terms do relate to each other. Please know the definitions of those terms. Now, normalizing pH, this is how you are able to regulate the pH by controlling your ventilatory rate. Ventilation is controlled through the medulla and the pons, as you already know now. You have to constantly measure the chemical concentrations in your blood using chemoreceptors. So, if, let's say, you have a lot of CO2 buildup in your blood or tissues, high CO2 means you're going to have a low pH. This low pH will send a signal to your brain to start hyperventilating. You're going to start breathing faster to blow off CO2 faster. Now, if you look at this equation, if you get rid of the reactants of this equation, this whole equation will want to push to the left side to balance out the loss of CO2. Why is it a loss? Well, you're breathing it out, we just said. You're hyperventilating, which means breathing faster, which means you're blowing off more CO2. And if you expire more CO2, you're going to be losing this reactant, and this whole equation will want to push to the left. Why is that good for us? Well, because we just said you're acidosis. If you're in acidosis, that means you have a lot of acid. You want to get rid of these guys. If I can push this equation to the left, that means these guys, the protons, bind with bicarbonate to make H2CO3 and break down to H2O and CO2, and you can expire this out. So you're going to reduce the proton level in the blood and therefore raise pH back to normal. If you can understand this one, this is the same thing. Let's say you become alkalotic. Your body is going through a process called alkalosis. That means you're alkaline, you're very basic, which means you have too little CO2. And yes, there is such thing as too little CO2. You do need some CO2 in your blood to balance that pH. If you don't have enough CO2 in your blood, what is the easiest way that you yourself right now could do to raise that CO2 concentration back up? Well, you could hold your breath or do one thing called hypoventilation. Breathe much more slowly. The slower you breathe, the more CO2 that accumulates in your blood, and the more CO2 you have here, the more it's going to push this equation to the right side to make more protons, and it's going to raise that H plus concentration, therefore lowering pH back to normal. So, big picture in this slide. If you're in acidosis, your body will respond with hyperventilation. If you're in alkalosis, your body will respond with hypoventilation. This would be a great test question to have, so it's important that you understand this. Let me know if you do not. That is the end of this slideshow. This is the respiratory system. Be sure that you utilize me as a resource. Also, the tutoring center, I sent an email that they are open for tutoring, and they are going to do Zoom, FaceTime tutoring, whatever program you have. So contact them if you need tutoring. If not, just contact me. I would love to do some office hours over FaceTime or Zoom. Let me know what you need. It's been going very well so far. Otherwise, you guys don't have a test coming up anytime soon. I think it's in 2 weeks or so. And I will send out a mass email for that in the next week and let you know how we're going to do that. I did send a mass email out asking if everyone had a laptop, Wi-Fi access, and a webcam, because you will need the webcam so that I can monitor the test taking. Your next test, I believe, again, is in 2 weeks. And the last piece of material we have is to cover the renal physiology, which is going to take us a good week and a half or 2 weeks because I'm going to go through it really slowly. Anyways, email me if you have any questions. If not,